Hi, and welcome to 9.2, the Impulse Momentum Theorem. In this lesson, students will be able to describe the concept of the impulse momentum theorem and use it to calculate physical quantities in different scenarios. So here are a couple of scenarios where you might be thinking about the impulse momentum theorem. I typically would do this in the classroom, and I would say in pairs, use the terms force and or time to describe how the following devices help protect people from injury. So in the first one, this is like a stunt airbag that stunt people would use. This is well, it's not an animation, but it's a picture showing the crumple zones and the different materials used for a frame in a car. So why would you want certain areas of the car to be designed to crumple? And then this is obviously a football helmet. So I'll pause the video here. You could either find somebody to talk to about this, and remember to try to use the words force and time in your description. How do these things, these different scenarios, help protect people from injury? Okay, hopefully you had enough time to think about it. So in this first one, it's an airbag. So you could say that, oh, look at this person, they're going to fall. Would you do that without an airbag? No, because the ground doesn't give as much, right? So the time of impact is increased. You're slowing down over a longer period of time, and this actually decreases the force required to slow you down to a stop. If you give more time to come to a stop, then you need less force to come to a stop. If the airbag wasn't there, you wouldn't do that, and you would need more force because it would be a shorter amount of time. In this crumple zone, for this, look at that. It's designed, the front of the car is designed to, look how much it deforms. It's weakened on purpose. And why would they make the front of the car weak? Well, the inside is strong. All right, see how the inside of it does not deform as much as this does? All right, what's happening is you're increasing the time of impact, which decreases the force necessary and force felt by the person. By the way, there's also an airbag going off. That airbag also increases the time of impact, thereby decreasing the force necessary to come to a stop. And same with the football helmet, you could see all the padding inside of the helmet. It's not just that, oh, there's a hard surface there. Really, the hard surface is there so that it can hold the padding, and the padding is the thing that's doing the work. Yeah, you need the hard surface there as well. But the padding is really the unsung hero of the football helmet because without it, your head would get bashed in pretty good, but luckily that it's there. So good. So the whole idea is that you want to increase the time of impact so that you can decrease the force necessary to come to a stop. I wonder if we can describe this using some physics terms and maybe a little bit of formulas and math. So let's add to the definition of impulse. We'll get the full picture now. We started off by saying, okay, just any change in momentum, if how much did the momentum change by, that's due to the impulse. Well, what is the impulse actually doing to change that momentum? I reworded the first sentence and I added in this bolded one. So it says the change in momentum brought about by a force acting over a period of time. That is the definition of impulse. You're changing your momentum because a force is acting over a period of time. Impulse is the product of a force and the time over which the force acts. Product meaning multiplication. Okay, so you're multiplying the force and the time together. And again, impulse is a vector quantity because we have this force acting in a direction. And now you'll see why it's known as a Newton second is because you have the force times the time. Newtons times seconds, that's equal to the unit for impulse. But where did we get, okay, so force times time. All right, in those examples, we said, okay, if you increase the time of impact, that decreases the force necessary in order to have the same change in velocity you're coming to a stop, in order to have the same change in momentum, in order to have the same impulse, all three different ways to describe the same thing. But where did that come from? Let's derive it. So the impulse momentum theorem states that when a net force is applied to an object over a certain time interval, the force will cause a change in the object's momentum. I like that definition. That's nice. So, okay, impulse is your change in momentum. And most of the time, if you're changing your momentum, it's because you're changing your velocity, not because you're changing your mass, although that would also change your momentum. And we've seen delta V before in the definition for acceleration, which is your change in velocity over time. So yeah, if we're changing our velocity, we are definitely accelerating. We know that. Well, how can we rearrange this equation? If you solve for delta V, you get this term, AT. And if you plug that in, then you're left with mat. But nobody really likes mat, so let's change it some more. Is there something that looks familiar in mat? All right, the net force is equal to ma. That's Newton's second law. So instead of writing ma, we'll just write force. And you guessed it. That's how we know that the impulse is equal to the force times the time, because it comes from the definition for acceleration, your change in velocity over time, and what we know about Newton's second law is that the net force is equal to the mass times the acceleration. All right, so those come together into this like big long thing, this statement that says that your impulse is equal to your change in momentum, and because you're changing your velocity, which is brought about by a net force acting over a period of time. That's really what's causing this change in momentum, is the force. And it's not an instantaneous thing. Even at like a ball hitting a bat, you'd think like, oh, that's super fast. But it does. The ball is in contact with the bat for a measurable period of time. And actually, there's some videos in the extension folder that like there's like a slow-mo video of a ball hitting a bat, and you can see that to the naked eye it looks like it's instantaneous, but we could actually find how much time the ball is in contact with the bat, multiply it by the force. That'll give you your impulse. So where is that big long theorem? It's going to be on the back page. Where is it? Over here. All right, so they tell you the key things, that the impulse changes your momentum because you're exerting a force over a period of time, but they leave out one of the things that we wrote down. Because you're changing your momentum, most of the time that's because you're changing your velocity. So if you want, you could write in equals m delta v, and then this will give you like a good tool in your tool chest to tackle most of the impulse momentum problems that come your way. All right, so I typically at this point do a demonstration in the classroom where I ask 2 student volunteers to hold up a sheet. So there are the brave volunteers holding the sheet, and then I ask another person to throw an egg at the sheet in the classroom. All right, there they go, and the egg is gonna go, whoa, into the sheet, and it actually doesn't break. I have like softball players, baseball players throwing this egg as hard as they can at the sheet, and the egg does not break. What the heck? Is it a hard-boiled egg? Is that why? No, it's a raw egg. And to prove it, I would never do this, of course, but I could repeat the experiment, but instead of having a sheet there, the person just throws the egg at the chalkboard instead of the sheet. You know, you have to repeat the experiment with the different variables there. I would never do that, of course, and then the egg gets everywhere. That would be gross, and somebody would have to clean that up. I definitely would clean it up if I did that. But yeah, so what about the sheet protects the egg? I wonder. Maybe it's because the sheet increases the time of impact, which decreases the force so that the egg doesn't actually break, because we still have the same mass, the mass of the egg. We're still changing the velocity by the same amount. You have some initial velocity here, and the final velocity is 0, even when there's the chalkboard there or the sheet. Both scenarios are the same. Very fast, 0, same change in velocity, same mass, that means the change in the momentum is the same and the impulse is the same. What's different is how that impulse is acted on. So the force is less when there's the sheet because the time of impact is more because you want to get the same impulse when you do the multiplication together. So if the force was 5 newtons on the chalkboard, and let's say, I mean, it's not 2 seconds, but let's keep the number simple. If it's 2 seconds there, all right, for the chalkboard, and then let's say it's 5 seconds for the sheet and 2 newtons there, you still get an impulse of 10 newton seconds. Graphically, it looks like this. So we have the sheet and the wall. We have the force on the y-axis, x on the time on the x-axis. So you want to exert a force over an amount of time in order to change the momentum. That's the whole idea behind the impulse momentum theorem. How you do so can change. So for the sheet, it's acted on, the force is acted over a longer period of time because the sheet has like more give to it. The wall is a very short amount of time to get the same change in momentum. And you could see, well, we'll talk about that later. It says the impulse is the area under the curve. And if you calculated both those areas, they would be the same. So it's the same impulse, but it's a different force and a different time. There's less time of impact here, so that means that you need a higher maximum force in order to get the same impulse. You want to come to a stop, and that higher force exceeds the force required to break the egg. If it's over a longer period of time, the maximum force that you reach is less than the force required to break the egg. And that's why it's a cool demonstration of the impulse momentum theorem. So let's do an example. It says a force of 50 newtons is used to slow down a 100 kilogram cart. The force is exerted on the cart for 2 seconds. What is the impulse acting on the cart? And what is the change in velocity? Let's start by writing our given information as always. And this is super important when you're doing impulse momentum theorem problems. The mass is 100 kilograms, the force is 50 newtons, the time is 20 seconds. Now, what are they looking for? J. Okay, what is the impulse acting on the car? Don't forget that impulse is J. So the first thing I'll write out the whole impulse momentum theorem. So the technique I like to do is you just pick out the 2 pieces that you need. There's 4 different pieces to this equation, but we only want to pick 2. So what do we need? We know, so I start with like, what are we looking for? I'm looking for J. So I'm going to rewrite, okay, I want the impulse is equal to, and then I have a choice. Look at the information that they gave you and see if you could figure out what the next piece I'm going to use. So even though they tell you what the mass is, and it might be tempting to try to do this, do you know information about the change in velocity? I would say no, you don't really know what the initial was, and you don't know what if they even come to a stop, you just know that they slow down. So that's not going to help us. We definitely don't have any information about the momentum, but we do have the force and the time. So I'm going to use that. I'm going to use J is equal to Ft. And for now, we could forget about all this other stuff. So that's what you do. You look at your reference table, you write down the given information, and you pick out which of these, I need 2 of them to make an equation. Just pick out the 2 that you need for each scenario. Each scenario is going to be different. So then it's just a matter of multiplying 50 times 20. So the impulse is equal to 1,000. What are the units for impulse? Well, this is 50 newtons and this is 20 seconds, so I would call it 1,000 newton seconds. Is it wrong to say A kilogram meter per second? No, because that would tell you how much we changed your momentum by. Our momentum changed by 1,000 kilogram meters per second. That's a different way to think about the impulse. But typically they'll say 1,000 Newton seconds for the impulse because that'll show that you understand that it's the force acting over a period of time. Okay. Then it says, what is the change in velocity? So now we have another piece of information here, and we're looking for just delta v, the change in velocity. I like that they asked it like that because I don't have to worry about the initial and final. I just solve for delta v. So again, we want to use this, and then we have our choice. We could either use this because we have the force and the time, or you know what, we just solved for the impulse. So let's make our equation a little bit easier by just writing the impulse is equal to m delta v. That's perfectly fine as well. So 1,000 is equal to the mass times delta v, and then you divide. The change in the velocity is equal to 10 meters per second. So we know that we changed our velocity by 10 meters per second. We don't know what the initial velocity was or the final velocity, but we know that it changed by 10 meters per second. By the way, this could have even, maybe this person turned around. Maybe they were initially traveling with this velocity, the positive direction, and then the force acted for so long, over 20 seconds, maybe they slowed down to a stop, turned around, and had some velocity in this direction. Let's say maybe this was positive 5 meters per second, and then this became negative 5 meters per second. The change in your velocity is still 10 meters per second. So that's, remember, it can go in the other direction, just like before, but it doesn't have to. Maybe we just started at 10 and slow down to 0, or started at 20 and slow down to 10. But that's the idea. Okay, so an 80-kilogram hockey player is skating across the ice at a speed of 5 meters per second. What is the magnitude of the average force required to stop the player in 0.25 seconds? And how far does the player travel as they come to a stop? So we'll write the given information down. Remember, if they come to a stop, that means the final velocity is 0 meters per second, and the time is also given to you, and they're asking for the force. So again, if you're looking at the whole theorem, we know that we're going to want to include this portion because we want to know what the force is. They're looking for the force. What other piece of information is useful? Well, we know m, and we know the change in the velocity, the initial and the final, so we can use that. Now you just plug in. Remember to do the final minus the initial over here, and you can solve. You end up getting negative 1,600 newtons. Okay, why a negative number? Because our initial velocity we made positive. And if you're going to slow down to a stop, it makes sense that your force is in the negative direction, slowing you down. Try this practice one. It says a 2,240 kilogram car traveling to the west slows down uniformly from 20 meters per second to 5 meters per second. How long does it take the car to decelerate if the force on the car is 8,410 newtons east? How far does the car travel during the deceleration? So make sure that you're paying attention to the directions, west and east. Pause the video and try it on your own. We'll start by, hopefully you did it. Did you do it? Try it on your own first. All right, I'll start by writing the given information. West means negative, east means positive. Right, west, east, negative x direction, positive x direction, that type of thing. One thing I'll point out is the wording of this says, how long does it take? That's the wording for time. Some people see long, and I understand this says, okay, that sounds like distance to me, but that's what part B is asking. How far does it travel? So if it says, how long does it take? They're looking for the time. All right, so we have our givens and our unknowns. Let's write the whole thing. And we'll pick out the parts of the theorem that we want. We're looking for the time, so we definitely want this one. And it looks like we have enough information to do the m delta v. And you get a time of about 4 seconds, 3.9952. Okay, so now that we know the time, we'll be able to use a kinematic equation to find the displacement given the initial velocity, final velocity, and the time. Which equation would you use to find the displacement? Oh, not that one. Don't forget about the secret formula. Yes, kinematic equation review. And you get a displacement of negative 50 meters. Why is it negative? Because you're traveling to the west in the negative direction. All right, fun times. That's about it. Thanks for watching and have a great day.